Let's pick up where we left off on Thursday. Let's reassess what we know about entropy so far. Okay? The big statement I gave you with respect to entropy is the statement of Boltzmann's equation. That the absolute entropy of a system is given by a constant times the natural log of the number of microstates. And that constant is a constant that goes as the reciprocal of the Avogadro's number. Okay? And we did all sorts of stories on Thursday of last week dealing with flipping of coins and such as that, and talking about how we could describe a state of coins that are all heads or a state of coins that are all tails as ordered, and a state of coins that were two heads, two tails as disordered. Okay? I said this is a really unrealistic model for a chemical system. So let's apply this model to the most unrealistic state of a chemical system, and then to much more realistic states of a chemical system, and see what we're working with. Okay? One extreme is what I'm going to call a perfect crystal. The idea of a perfect crystal is I have something that's as perfectly ordered in the solid state as I can possibly get. When you think of crystals, what you're thinking about are states such that you have a lattice of positive and negative charges all lined up next to one another and all locked into position. So there's not any real room to move around. And the more perfect that crystal is, the less room there is to move around. And I can model that perfect crystal as if I have one microstate. Just like I flip the 4 coins, and it's very unlikely that all of them turn up heads. Just like if you've actually got into the homework, you could imagine flipping all of the coins and having all of the coins out of 100 or 1,000, all those coins turning up heads. And the extreme unlikelihood of that. Okay? If you imagine a mole of a crystal in a perfect frame so that there's only one possible microstate that the whole thing can have, that is what defines perfection. And so what I need to do is 1.381 times 10 to the negative 23rd times the natural log of 1. I told this story when I was in class on Thursday, I think. But if I didn't tell this story when I was in class, let me bring up Google. Let me search for a calculator. And let me go through 1.381 times 10 to the negative 23rd times the natural log of 1. Anybody know what that's going to wind up being? Natural log of 1. Any logarithm of 1 gets me something that's very much 0. Okay, so it doesn't matter what this number was over here, because the natural log of 1 is 0, the whole mess is winding up being 0. Okay, I bring out the calculator just to re-emphasize. If you haven't played around the calculator and gotten an instinct for how these logarithms work, it's a really good thing to do so. And I'll go the other way with how I consider these logarithms in a moment. So the entropy of a system with a single microstate is 0. This is one of our laws of thermodynamics. Now, because of the way that I have been presenting these ideas and the order that I'm going through, I'm actually presenting to you the third law of thermodynamics before I ever get around to presenting the second. They're not dependent on one another. There's nothing in the third law that's based on the second law. So this is a completely appropriate thing to do. It's just a little bit weird. The absolute entropy of a perfect crystal is identical to the entropy of a system with a single microstate. That entropy turns out to be 0. It gives me that lower bound for how I'm going to be thinking of entropy of a system. Okay? And for any type of bulk matter that I might study, solid, liquid, or gas, I'm going to run across systems with entropies greater than 0. Now, what is the closest thing that you can think of to a perfect crystal that might appear in nature? Consumerist society tells us that this type of object communicates messages, especially when given with love and affection. Because, man, if we have something we want to say to the ladies, we say it with what? Boy, I know. I know so well, right? Put it this way. What does K Jewelers say you should say it with? Love isn't perfectly crystalline or even approach it. Diamonds. Diamonds are, when you look at them, they're tangible and visible in their crystalline perfection, or what appears to be crystalline perfection. Okay? That's the type of thing that you should be connecting with this idea of the perfect crystal. That's the closest thing we can come in nature to that. And if you actually go to our handy dandy tabulation of thermodynamic data, and you look up and down the column of thermodynamic data, now I have to be honest, I have to be plain. There are some stuffs in the thermodynamic data that show off negative entropies, that show off entropies that are lower than what they expect to be. You'll find that all of those stuff are ions in the aqueous phase, and they'll always come alongside some other ion in the aqueous phase. But when we actually look at all of this stuff in this tabulation, the solid phases are the ones that have the lowest entropy. And among the elemental stuff, diamond will have the lowest entropy of them all. Diamond will have an entropy of 2.4 joules per mole per Kelvin. So here's the flip side that I want to describe. How many microstates does 1 mole of the most perfect crystalline stuff we can imagine in nature have? Okay? And that's going to be my other extreme tale here. How many microstates in 1 mole of the most perfect crystal I can think of in nature? Okay? Now, I'm pulling a little bit of a Professor Strick by talking about 1 mole of stuff. Is I'm already preloading this with 6.022 times 10 to the 23rd atoms of stuff. And that would imply that if I can talk about different states in each one of those, I'm already preloading this with 6.022 times 10 to the 23rd microstates. Okay? But let me go through the argument. Okay, I know S is equal to 2.4 joules per Kelvin for 1 mole. I know K sub B is a constant. Okay, I need W. I need to get W by itself. How do I go about getting W by itself? What algebraic manipulations do I need to do to isolate W? Well, the first thing I need to do is isolate the natural log of W, right? So what do I need to do to get the natural log of W by itself? I need to divide both sides by K sub B. Okay? Now, W's buried underneath that natural log thing. And so somehow algebraically, I need to undo that natural log thing. How do I undo the natural log? This is where the exponential function comes in. I need to raise e to the value of both sides of this equation. E raised to the s over k sub b power is equal to e raised to the natural log of w power. And e raised to the ln of something's power is that something. E and ln undo one another. Okay? Because the effects of E and ln cancel one another out. Rhetorical question for folks on Zoom. You don't have to put it in the chat. How many of y'all have recognized a relationship like that before and used a relationship like that before a whole lot? Okay. Part of the reason I am I'm saying, hey, go into Alex and practice with the Alex stuff is so you can build up math skills to the point where you can come across these logarithms and you can get used to these logarithms. For reasons that are going to become really obvious here shortly, I'm not that worried. Excuse me. For reasons that will become obvious really shortly, I'm not that worried about this algebraic manipulation today. But I will be worried about this algebraic manipulation in the future. And I want you to recognize it and be able to do it. Okay? But W is equal to E raised to the S over KB power, which is equal to, the S is 2.4 joules per Kelvin, divided by 1.381 times 10 to the negative 23rd joules per Kelvin. I mucked around with this a little bit earlier. .4 everybody divided by everybody in 1.381 times 10 to the negative 23rd. Stick it in parentheses if it makes you feel more comfortable with it. Okay? And when I go 2.4 divided by 1.381 E negative 23 in my calculator, I'm going to come out with E raised to the 1.74 times 10 to the 23rd power. Let me see if I can write that out. 11, 12, 13, 14, 15, 17, 18. Oh, that's 15. This is 18. This is 21, 22, 23. And E is a tiny number, 2.71828. Okay? But even a tiny number raised to the 174th billionth trillionth power. I mean, anybody ever tried to put a calculation like that in their calculator before? Hey, I've got a calculator up here on the screen. Let me go ahead and bring up that calculator. Okay. 2.4 divided by 1. Oh, I hear you. 0.381 E minus 23. There's the 1.74 times 10 to the 23rd. And the inverse of the natural log is the exponential function. Exponential of 1.7. I could do 3787, but I'll just do 1.74 E to the 23rd. What's the calculator going to give me? If it's yours is a less sophisticated calculator, it's just going to come back with error or math overflow or yo mama core dumped or something like that. The Google calculator is a little bit more sophisticated. It comes back infinity. Okay? It's not really infinity. It's just a number that's so daggum big that the calculator doesn't know how to handle it. So let me put that as the answer here. A number of microstates too large for even Google's calculator to handle. And I think that's a really big deal because, again, Google is named after the number that represents 10 to the 100th power. Google is named for a really big number. You would think a Google calculator would handle really big numbers well, and no, and no. But here's the thing, okay? That's the number of microstates. That number that's way too big is the number of microstates for 1 mole of the closest thing we can think of in nature to a perfect crystal. 1 mole of diamond. Okay? And that was, by and away, the smallest number on that list of absolute entropies of matter. Every other absolute entropy of matter got into the tens or the hundreds of joules per Kelvin per mole. Okay? if this really tiny entropy gets me too many microstates to handle, how many more microstates am I dealing with when I deal with a gas? A crazy, crazy amount is the answer there. Okay? So we have to deal with this problem when we deal with the Boltzmann equation and its derivatives here, that it talks about this number of microstates. And it talks about these microstates as if these microstates can be counted. And when we get to dealing with real chemical systems, not only are they too many for us to count, they're too many for our calculators to count. And that gives us trouble. And that puts a limitation on how we can use the Boltzmann's equation to describe entropy. We need a different way to describe entropy. The problem with the mole and other quantities similar to the mole is that they're describing an amount of matter that is in bulk, that is gathered together, and that we can't just manage dealing with atom by atom by atom by atom. 6.022 times 10 to the 23rd atoms is a large number of atoms for us to comprehend. We've dealt with this reality, right? And so assigning individual states and even describing how those states can flip back and forth for that number of atoms really gets to be a crazy, crazy concept. So let's talk about a more realistic way to describe the entropy of bulk matter. And let's talk about it in terms of a glass of water and let's consider what happens when that glass of water evaporates. Okay? Or to put it in equation form, H2O in the liquid phase being transformed to H2O in the gaseous phase. Now I want to talk about two different parts of this overall system that I'm working through as this is going on. I want to talk about the system of water molecules. And those water molecules are absorbing or releasing energy. And those water molecules are going through a phase change that make them do this thing or that thing. And I want to talk about the beaker and the air and other nature that surrounds that water as the water's surroundings. And to completely study what's going on with the entropy of this system, I want to spend time focusing on the individual water molecules themselves and how the water molecules are changing in entropy. And then I want to think about the nature surrounding these water molecules and how that nature surrounding might be changing entropy as well. And in describing these two parts of nature, the nature of the water molecules themselves and the nature of everything else surrounding the molecules, I'm going to come up with a complete description of what's going on with the entropy changes in this system. The entropy change in the system has been studied over great periods of time and has been tabulated. And I know what this entropy change in the system is when I deal with 1 mole of water molecules in the liquid phase evaporating and going into the gas phase. And I can deal with this in the same way that I've dealt with Hess's law in the past. I can take the entropy of the products and subtract it from the entropy of the reactants. The standard entropy of products minus the standard entropy of reactants is the entropy change in the system. That's what Hess's law tells us. Well, hey, in this transition, what are the products? H2O in what phase? In the gas phase. So I can go ahead and replace products here simply with the entropy of H2O in the gas phase. And likewise, I can replace reactants here with H2O in the liquid phase. And it's 1 mole of each stuff. Those are quantities I can look up, right? Let me go to my tabulation. Okay, I need to go down to hydrogen and I need to look up water. Are y'all noticing how often I go to this table? I spend a lot of time looking at the values on this table. I'm going to spend more time looking at the values on this table as I move forward. Okay? And I really value having this table around, and I make sure that I distribute this table to each of y'all who are actually doing work dealing with this material. Here are my lines for liquid water and gaseous water. And I'm now looking at the column that's on the far right labeled standard entropies. The standard entropy of water in the gaseous phase is positive 188.8 joules per mole per Kelvin. The standard entropy of water in the liquid phase is 70 joules per mole per Kelvin. Now, is this surprising at all, these values? What would I expect to be more disordered, water in the liquid phase or water in the gaseous phase? Definitely water in the gaseous phase would be more disordered. Water in the liquid phase is confined to the volume it holds in the container. Water in the gaseous phase is spread all the way around. Gas phase is more disordered than liquid phase, which in turn is more disordered than solid phase. Okay? So the entropy change in the system is the standard entropy of water in the liquid phase minus the standard entropy of water in the liquid phase. I should say that again. The entropy change in the system is the standard entropy of water in the gaseous phase minus water in the liquid phase, because the gaseous phase are the products and the liquid phase is the reactants. It's a pretty straightforward computation. (188.8 minus 70 is 118.8. Okay? That's the easy bit. That's the ordering and disordering of the individual molecules. But now what we do when we talk about the entropy change in the surroundings is we talk about the entropy change in the energy that gets transferred from the system to the surroundings. Now, y'all know about the energy change in evaporating water. You know about it because you've worked out, most of you, at some point in time, and you've done some strenuous manual labor, and that strenuous manual labor has made you sweat. And what's the purpose behind you sweating? What do we hope happens when we sweat? That counteracts what we caused us to sweat in the first place? We hope we cool down. Sure. Okay. We hope that the process of sweating removes heat from us so that the individual water molecules can absorb that heat in the process of evaporation. It's called evaporative cooling. It's one of the things that makes water such a unique compound and so important to our day-to-day living. So, how much heat energy does water absorb as it goes through this transition? Well, what quantity do we have that's tabulated that tells us about the amount of heat energy that gets absorbed at constant pressure? The entropy change in the surroundings is a function of heat transfer, or alternately, a function of enthalpy change between the system and the surroundings. What I'm going to need to do is I'm going to need to find the heat transferred into or out of the system at the temperature of the surroundings. That particular construction, by the way, is the place where joules per Kelvin comes from. Heat transfer at a given temperature is representative of entropy change in the surroundings. Now, where do you think the negative sign comes from? I could have been really, really boring and just written this as delta S of the surroundings is equal to Q of the surroundings over T of the surroundings. But I wrote it as negative Q of the system instead. Because ultimately, in order to cool us off, this evaporation of water is going to be taking energy up. It's going to be absorbing energy. Where does that energy come from? It comes from everything that surrounds the water, including our foreheads when our foreheads are feeling really blasted hot. Evaporative cooling is by evaporating the water is absorbing heat. The water is absorbing the heat that we release. And that's the mechanism by which we cool off. Now, it's not obvious how I'm going to go about computing a Q of the system, but hopefully it can be a little bit more obvious how I could go about, let me just write this as an OR. Hopefully it can be a little bit more obvious how I can go about computing a delta H for the system. Okay. And I've got those H values for specific materials. I've got those tabulated, right? Oh, here I go again, right back into my standard tabulation. Somebody else recognized cool the body down before I said sweating. Thank you for that. In my leftmost column, my delta H standards, I've got a delta H for water in the gas phase, and I've got a delta H for water in the liquid phase. In the gas phase, it's negative 241.8. In the liquid phase, it's negative 285.83. Okay. So let me go through the exact same Hess's law arguments to get the delta H for the system that I went through for delta S of the system. Let me go products minus reactants again. And again, the delta H for gaseous water was negative 241.8 kilojoules per mole. And then the delta H for liquid water was negative 285.83 kilojoules per mole. Negative of a negative is positive. 285.83 minus 241.8. That's color consistency. That's going to be equal to 44.03 kilojoules per mole. Now, that's not quite what the enthalpy of vaporization story tells you about the delta H for the system when we transform. There's a slightly different number that you get out of the enthalpy of vaporization. And that'll get you different results as we go through, but this will actually do very well for us for this particular purpose. Okay? So let's go from delta H of the system to delta S of the surroundings. Okay? What's an interesting temperature to study the evaporation of water at? Somebody come up with a temperature I should study. Feel free to dump a temperature into the chat as well, Zoom people. There's a temperature coming into the chat. What do we got? 17 degrees Celsius. Oh, that's an oddly specific temperature. But remember, I can't do this in degrees Celsius because the units of delta S are joules per Kelvin or joules per mole per Kelvin. So instead of saying 17 degrees Celsius, what I need to say is 290 Kelvin. Or if I really wanted to be precise, 290.15 Kelvin. But 290 will do for us. Okay? So delta S of the surroundings for 17 degrees Celsius will be negative 0.15. By the way, I need to have this in joules per mole per Kelvin. What should I do with delta H if I need to have this in joules per mole per Kelvin? And delta H is in kilojoules. Yeah, this is the single most obnoxious thing about having to do some sort of computation with delta H and delta S is that delta H of the system I need to take as 44,030 joules per mole. Because I'm going to be dividing that by 290 Kelvin. Negative 44,030 divided by 290 gets me a delta S of negative 152 joules per mole per Kelvin. Now, 17 degrees Celsius is a really typical temperature, particularly on a day like today, which is still not quite fully out of winter. It's a typical temperature of our DI water coming out of the tap. Do we expect the water we get coming out of the tap to readily evaporate, especially when it comes out of the tap relatively cold? That doesn't seem like something that would readily happen. And it doesn't. Delta S of the universe turns out to be a standard for how readily a reaction like this will happen. And delta S of the universe, let me actually put this in green. It's equal to delta S of the system plus delta S of the surroundings. The system delta S I computed earlier in blue, that was my 118.8 joules per mole per Kelvin. My delta S of the surroundings is what I just computed. It's negative 152 joules per mole per Kelvin. So delta S of the universe, delta S of the system and the surroundings together for this story is negative 33. 33? Yeah, 33 is what a good number to put to it. Okay? And so even though I've got a lot of disorder coming out of the transition of the liquid to the gas at very cold temperatures, I actually wind up absorbing so much heat, releasing so much heat to the universe that I actually make, absorbing so much heat from the universe so that the water can evaporate. I wind up absorbing so much heat from the universe that the entropy change from the universe is substantially negative. And this does not represent spontaneous evaporation at 17 degrees Celsius. But then again, 17 degrees Celsius, that's pretty doggone cold. I wouldn't expect water to spontaneously evaporate at that temperature. What temperature would I expect water to evaporate at? Every time. It may evaporate at temperature slightly cooler than this, but I know it will evaporate if I take the temperature and raise its temperature up to, thank you, chat, 100 degrees Celsius. Absolutely. And as it turns out, if you take this right here and replace it with 373 Kelvin, this number is going to decrease in size. I make the denominator bigger, I make the quotient smaller, right? And it will decrease so much that it will flip the sign of the entropy of the universe over to something positive. Okay? Try this computation on your own with 373 Kelvin in this space. Okay? And come out with a value. You can play with it on your own time. Okay? But you'll find that that gives you a positive delta S of the universe at 100 degrees Celsius. Whereas we reasonably expect a negative delta S of the universe at 17 degrees Celsius. We're getting told a story here in studying this reaction about how readily we see these processes happen at different temperatures. And another way to write this delta S of the system plus delta S of the surroundings, the way we've computed it, is that delta S of the universe equals delta S of the system minus delta H of the system over the temperature of the surroundings. There are a couple of different problems in the homework that actually are based on this very idea, that we have some sort of heat transfer from the system to the surroundings that feeds into how we actually compute the entropy change of the surroundings. And we get the entropy change of the system from the actual nature of the reorganization of the atoms and molecules in the system, and that comes from our tabulated values. Okay? But a statement like this ties in directly with the second law of thermodynamics. Now I'm getting close to the end of the period here. So I'm going to take this opportunity to really commend your textbook to you. Your textbook gets the material on entropy right. It gets it so right. And the examples are good and the phrasing is good. Okay? And how I want to frame the second law of thermodynamics is I want to come right after what your textbook provides. That's even more compact than what I have in the 8 a.m. hour. I like that. You may have heard the second law of thermodynamics put in front of you before in a form like the entropy of the universe is always increasing, or the universe is always getting more disordered, or such as that. I want to say that the second law of thermodynamics applies directly to spontaneous reactions. We define spontaneous reactions as reactions that are capable of going forward without external energy input. Now, I don't care over what time. If the evaporation of water is spontaneous in a given condition, that evaporation of water is going to happen. It may happen in a couple of minutes. It may happen over the course of an hour. It may happen over the course of 4 to 5 days or longer. But if it happens and it didn't require external energy input for it to happen, it's spontaneous. And spontaneous reactions cause the entropy of the universe to increase. That statement that any reaction is spontaneous, if that reaction causes the entropy of the universe to increase, that statement is the second law of thermodynamics. Okay? So, we are studying what makes reactions spontaneous. Much of the next phase of this course is going to be given over to the types of conditions that make chemical reactions spontaneous. There are two conditions in this expression here that make chemical reactions spontaneous. The first condition is if delta S of the system is greater than 0. If the entropy of the system is increasing, then that favors spontaneity. But the problem with our particular transformation of liquid water to gaseous water is that transformation required the absorption of energy. And that absorption of energy did not favor spontaneity. I needed to be in this condition where I had a process happening that favored spontaneity if I was going to get a conclusively spontaneous reaction. And that's represented by delta H of the system being less than 0. The evaporation of water, because delta H for that system is greater than 0, is, if delta H is greater than 0, is that endothermic or exothermic? If delta H is greater than 0, not what I've got written on the board, is that endothermic or exothermic? That's the absorption of heat energy. That is absolutely endothermic. Okay? So, delta H of the system is an exothermic reaction. System releases heat energy to the surroundings. And if delta H is negative, negative of a negative is a positive. And that is also something that will cause delta S of the universe to increase. Delta H of the system being less than 0 is something that favors spontaneity. Everybody got that? Questions right now? Two things before I let you go. Thing one, I really want to commend your textbook to you. Okay? Number one, your textbook goes through the laws of thermodynamics in order. It doesn't try to do third before second. It does second, then it does third. Okay? And for that reason, it very patiently develops the second law of thermodynamics in a different fashion. It reframes the entropy change of the universe in terms of delta S of the system plus heat transfer to the surroundings. And the other reason I want to commend your textbook to you is it's got really good examples in a slightly different language, so that if what I went through here today was confusing, the textbook may be a great deal more helpful to you. And the example in the textbook turns out to be the melting of ice, not the vaporization of water. So it's the same type of an example, just for a different associated system, or a different associated phase of that system. And it doesn't just tell the stories of entropy change to the system and the surroundings in terms of reactions from one phase of stuff to another phase of stuff. It tells those stories for full chemical reactions as well. One thing I haven't gone over is how you use the stoichiometric coefficients in describing these stories. Examples in the textbook will get you through that as well. Okay? So the textbook, always read the textbook, always read the textbook, always read the textbook. But really read the textbook here for this stuff. Okay? The other thing that I want to commend your attention to is that this is a story that involves the delta S of the system, delta H of the system, and the temperature of the surroundings. If the temperature of the surroundings and the temperature of the system are the same, the system and surroundings are at thermal equilibrium, then I can use this particular statement to describe another quantity. Okay? How many of y'all have heard of free energy? It turns out what I've been doing with this formulation of the second law of thermodynamics, using this entropy change of the universe to represent a spontaneity condition, is I've been setting up how I'm going to define the concept of free energy. In fact, you can do it yourself. You would just need to multiply everybody in this term by negative T. If you multiplied everything in this equation by negative T, you would get delta H minus T delta S on the right-hand side. And it turns out negative T times delta S of the universe is what we call free energy change, or the Gibbs energy change, more appropriately. So free energy is my subject matter for next time. Those of you who are Tuesday lab people, I'll see you in lab shortly. Otherwise, I'll see y'all on Thursday.